Hi, in this video, I'm going to talk about the common ion effect, and we're going to look at a couple of ALEKS problems involving how we set up the idea of using an acid-base equation to analyze reactants and products. So let's take a look at this idea, 17.1. Which is the common ion effect. Okay. Now, what we often see when we react an acid with a base is that we form water and a salt. Okay. That's generally the idea. So for example, HCl dissolved in water is a strong acid. NaOH is a strong base. Dissolve it into water, the two will react, right? That's called a neutralization reaction. We can treat this as a double displacement by taking the H plus and the OH minus to form water. And then we can take the metal ion from the base and the non-metal from the acid and get our salt out of that. Okay. Now, what we're going to look into is considering what these products are, in particular, the salt. We're going to be interested in that because as we move through this chapter, we're going to be doing pH calculations. And what we found at the end of chapter 16 is that a salt can be either acidic or basic, or it could be neutral. In this case, sodium chloride is neutral because the two conjugates, remember, this is the conjugate acid, and this is the conjugate base. Each of them comes from a strong base and a strong acid. The sodium comes from a strong base. The chloride comes from a strong acid. So they're very weak in terms of their effect on acidity or pH. Okay, so this would be a neutral salt. But we'll look at cases where the salt could be acidic or basic, and that will have an effect in terms of the acidity in more details. So let's take a look at a problem here. Here we go. And this type of problem is called identifying the major species in weak acid or weak base equilibria. Okay, so there's a lot of words in this instructions. They're trying to get across a lot of language here. What we're going to actually do is relatively simple, but let's read through it anyways. The preparations of two aqueous solutions are described in the table below. For each solution, write the chemical formulas of the major species present at equilibrium, and you can leave out water itself. You don't need to include water. Write the chemical formulas of the species that will act as acids in the acids row, the formulas of the species that will act as bases in the bases row, and the formulas of the species that will act as neither acids nor bases in the other row. You will find it useful to keep in mind that HF is a weak acid. So for this specific example, HF is a weak acid. So we're just concerned about the products. Well, actually, I should be more careful. I should be more precise than that. We're concerned with what's in the solution once the reaction is complete. Once the reactants have reacted, what is in the solution? So part of this will require us to do a little bit of arithmetic to figure out what's going to be left once the reaction has taken place. And then we have to identify whether something is an acid or a base or other. Okay, So let's take a look. In this particular example, what they tell us is that we're going to add 0.6 moles of KOH to 1.0 liter of 0.3 molar HF. Okay. And then again, we need to know what's going to be an acid. Is there going to be any acid? Is there going to be any base? Or is there going to be other? Or yeah, other, I guess is the word they use. Once the reaction is complete. So let's write out the equation, KOH. That's a base, right? That's a strong base. And then it's going to react with HF, which is a weak acid. Okay. So again, the idea here, at least for this one, would be to consider that, you know, your H plus is going to combine with your OH minus to give you water, right? And then your metal will combine with the non-metal to give you the salt. Okay. Now, we have numbers here. So this 0.6 moles is what we're starting off with here. And they don't tell us how many moles of HF we have, but they do tell us it's 1 liter. Remember, molarity is moles over volume. So if we want to find the number of moles, we just take the molarity and we multiply it by the volume. So that would be 0.3 moles per liter. Remember, capital M is short for moles per liter times 1 liter. Liters cancel, and we get 0.3 moles. Okay. They're not making the numbers particularly difficult to do here. They're making the volume 1 liter just so that you can do the arithmetic pretty easily. Now, here's what happens. These are going to react with each other. And remember, we have this idea of the limiting reactant from Chem 11, from the first semester of general chemistry. If you have one reactant that's in lesser amount than the other reactant, it will limit how much of the products you can get. So here's what will happen. This is the smaller value here. So this is the limiting reactant, right? Again, you know, you use those analogies like a sandwich. If we had 6 slices of cheese, but we only had 3 slices of bread, you can't get, you know, you can't get 6 sandwiches out of that, right? There's a limit from one of these reactants. So the HF is a smaller amount, so it's the limiting reactant. So that means that what's going to happen is it's going to react completely. But this one can only go down by the amount that the limiting reactant is in there, right? Can't go down by more than 0.3 because we don't have any more than 0.3 of the HF. So that'll give us 0.3 moles at the end. This will be gone. The limiting reactant ends at 0. But notice these go up, right? This one's going to go up by 0.3 moles. And this one's going to go up by 0.3 moles. Now they say don't worry about the water. They say don't worry about writing out the species for the water. Water is the solvent, so there's going to be a lot of water there anyways, so that's not a big deal. So we don't need to worry about that. I'll just put a little X there. But what about the KF? The KF started off as 0, but it went up by 0.3, so it's now at 0.3 moles. Okay. So now, once this is done, what do we have? This is left over, right? This is remaining. Okay. Now, KOH is a base, right? HF is 0. It's gone. So there's no acid there. Water, again, don't worry about it. But we also have 0.3 moles of KF. And that's an interesting issue, this idea of having KF. We're going to talk about that as we go through there, okay? It turns out that if we consider KF, It's aqueous, right? It dissolves in water. So that means it's really going to be K plus and F minus. Okay, it's really two things. Now, KOH is also two things. So actually we have to be, I'm going to be a little bit careful here because we have to think about how they want us to do this. Okay, good. So KOH is also K plus and OH minus. Okay, so it looks like what we have are three species, ignoring the water, three species left after the reaction is done. We have K plus, some of it is in the form of KOH. We have KF, some of the K is there as well. So that's the same species, that's just K plus. But we also have two other species. Now, OH minus is generally considered a base, right? And H plus or H3O plus, either of those, is generally considered an acid. But what about K plus? And what about F minus? Are those considered acids or bases? And it turns out K plus is not an acid or a base. But F minus is a base. Now, why is F minus a base? Here's what we do. Remember at the beginning it said HF is a weak acid, that one sentence in there. Okay, so if you have a weak acid, okay, so for example, HF, the conjugate base is going to act like a base. Okay. Likewise, if you have a weak base, for example, NH3, the conjugate acid, which in this case would be NH4 plus, it's going to act like an acid. Okay. So you have to know that the F minus is the conjugate base of a weak acid. And if it is the conjugate base of a weak acid, it will be a relatively, we have to be very careful about the language here, a relatively strong base, meaning that it will affect acidity. It'll make water basic. It's not a strong base, it's not OH minus, but it will have an effect on the acidity. Okay, so the fluoride ion will make water basic. But what about the potassium ion? I said that that's not an acid or a base. Well, it's the conjugate acid of a strong base. And this gets back to the last lecture, right at the end of chapter 16. You can review that if you want toward the end there. The point being that the conjugate acid of a strong base has no effect on acidity. The conjugate base of a strong acid has no effect on acidity. But the conjugate base of a weak acid is basic. And the conjugate acid of a weak, the conjugate acid of a weak base does make solutions acidic. Okay. So in this case, since fluoride is the conjugate base of a weak acid, it will make the solution basic. So here's what we do in terms of the notation of this particular problem. There is no acid left over. There's no H plus and there's no HF. It's all the HF has been used up. So there's no acids here. But in terms of the base, there's actually two. There's the hydroxide, which is clearly a base, but you have the conjugate base of a weak acid, and that's the fluoride ion. So that one definitely will behave as a base. So you can just separate them with commas. I don't think in the instructions it's said to do that, but you can just write a comma there. Now, what about the other? Well, the other is anything other than water that is not an acid or a base. So that's the K plus. K plus is the conjugate acid of a strong base. So it's not acidic or basic, so it would be other. Okay, and there's all your species. So notice what you got to go through here. You got to write the equation out, get your products, go through the arithmetic, and then identify which ones are acids, which ones are bases, and which ones are neither. So let's take a look at part 2. Part 2 is actually the same reaction. It's just they're going to change the amounts that are in there. So let me create a new one here. Okay, so it's the same reaction. All right, I'll write the base first. There's no reason that you have to write the acid first or the base first. You can write either one. Okay, so again, we're going to have our H2O and then KF. The only thing they did here is they just changed the numbers. They made this 0.36 moles. And then they made this one, okay, it's one, I'm going to do the calculation down here. 1 liter times 1.2 moles per liter of the HF. So that's 1.2 moles. Again, they're making the numbers easy for us. Okay, so those are the amount, and then we're going to run through the reaction, figure out what the acids are, the bases, and then the others. Okay. So which one's the limiting reactant? It's the KOH, right? The KOH is the limiting reactant because it's a smaller number, right? The equation is balanced 1-to-1, so it is more complicated if it's a 2-to-1, then you have to take that into account. But since this is a 1-to-1 reaction between KOH and HF, you just look at the smaller number. So this is the limiting reactant. Okay, so we subtract the limiting reactant from both. Okay, so what is that? That's 0.84. Oops. Yeah, I think that's about right. Let me just check just to make sure. 1.2 minus 0.36. Yeah, 0.84 moles. So that's how much is remaining. There's some HF left over, right? Again, it says don't worry about the water because water is the solvent. But this one's going to go up by 0.36. So we're going to have 0.36 moles of the KF. I mean, you know, technically it starts off at 0, right? So it goes up by 0.36. Okay, so here's what we're left with. We've got some KF left. So we've got K plus. We've also got F minus, right? KF is F, K plus and F minus. But we also have some HF. Okay. So we have H plus, but remember HF is an acid. It's a weak acid. So you really, what you get is you get some HF, but you also get a little bit of H plus and a little bit of F minus. It's mostly this because it's a weak acid. You get a little bit of this. So actually we've got quite a bit. We've got HF, we've got F, H plus. We also have F minus, although the F minus we already had there. We have both of them, right? So there's a little bit both there. Okay. So this one actually ends up with quite a bit of different things in it. Okay. Now, in general, oh, and actually, okay, yeah. Let me just make sure. I want to make sure here. Okay. All right, good. So now what we can do is we can come over here. Well, what is the acid? Well, HF is an acid, so we know that that's an acid. We know that we already said from the previous one that F minus is a base. There's no OH minus in this one, right? Because there's no, this was the limiting reactant, so the OH is minus, the OH minus is gone. But we have K plus. Okay. Now, the question then is, how do we deal with H plus? Now, I would argue that there is also some H plus in there, but the formatting of this particular problem, what they're doing is they're saying that if you have a weak acid, it's true you get a little bit of H plus, but we're not going to consider that the acid. We're just going to consider the HF the acid. I don't know. It's a little awkward to me to write it that way, but they would say just go ahead and put the HF here for the acid, put the F minus for the base, and then put the K plus for the base. I'm sorry, for the neither acid or base. Okay. Let's take a look at one more. identifying the major species. So in the first one, now we have a mole of HI, that's a strong acid, added to 1 liter of 0.8 molar NH3. That's a weak base, right? So you have a strong acid there with a weak base. So let's do that one first. The second one is 0.43 moles of HNO3, strong acid, 1 liter of 1.2. Now this one has 2 things in it. It has ammonia and it has ammonium bromide. So I'm going to take a look at that one also in more detail. That one's a little bit more complicated. But let's do the first one. Okay, 1 mole of HI and 1.0 liter, so and, of 0.8 molar NH3. Okay, and we want to know what's left over. Acid, base, other. Okay, so we have to do the reaction. HI with NH3. HI plus NH3. Okay, this one's the acid. This one's the base, right? So it's going to donate the H plus. So you're going to get I minus plus NH4 plus. Okay, now we have to do the numbers next. So the next numbers is we have 1 mole here. And 1 liter times 0.8 molar is 0.8 moles. Okay, we'll make these 0 at the beginning. So which one's the limiting? The smaller one. So you subtract 0.8 from everything on the reactant side, and you add 0.8 on the product. Okay, now we have a lot of stuff in there. We got 3 different things. We've got HI, we've got I minus, and we've got NH4 plus. Okay, however, HI is a strong acid. And what does that mean? When you take a strong acid, what that means is it dissociates completely. So you don't really have any HI in a strong acid. Strong acids really don't exist. They produce H plus and I minus, or hydronium and iodide. Okay, so this is what you've really got in there. You've really got H plus and I minus. The weak acids are undissociated for the most part. So now we have, for our acid, we have H plus. We have another one here. This is the conjugate acid of a weak. Let me write this a little more clearly, sorry. Conjugate acid of a weak base. So that means it's acidic. So we have another one. We have NH4 plus. Okay, we don't have any bases, because what about this one right here? You could say, well, wait a minute, isn't that the conjugate base? Yes, that's the conjugate base of a strong acid. Remember, if it's the conjugate of a strong, it has no effect on acidity. So that would go into the other category. The iodide is not strong, or it's not an acid or a base. Sorry, I don't say strong or weak. It's not an acid or a base. Okay. The only question I have here in terms of the Alex notation is, are they going to want us to write this as HI, or are they going to have us write it as H plus? It should be H plus. Oh my goodness. Okay, they're doing a little funky business here. What they're doing is they're saying that your H plus should be H3O plus, which I disagree with in the notation that they're using here, but whatever, that's what they tell you to do. I mean, it is true, it is hydronium, but there's no water in this reaction. So to turn that into hydronium is a little odd. Okay. In any case, if you see H plus, if you come up with H plus, make it H3O plus. All right. Okay, let's look at the second part. The second part is a little more involved because it's got a kind of an extra species there. Okay, so this one, you have 0.43 moles of HNO3, strong acid, and 1 liter of 1.2 molar NH3 and NH4Br. Okay, so you've got 3 things being added to here. And the reason we're doing that is that that's going to be an important issue. And when we get to the next section, which is called buffers. Okay, so let's take a look. First of all, this is a strong acid. So notice what I'm doing. I'm labeling things. Strong acid, weak acid, strong base, weak base. Okay, this is a weak base, right? But now this is 2 things. So I'm going to actually, just to be a little bit more organized for you, strong acid. Remember how I said you got to memorize those strong acids and strong bases so that you know the weak acids and weak bases by elimination. If it's not a strong acid, then it's a weak acid. If it's not a strong base, it's a weak base. So you got NH3, which is a weak base. And then you got NH4Br, which is a salt. And that's a salt, right? You've got the cation with the anion there. It's actually the product of an acid-base reaction. So if it's a salt, we're going to break it up into 2 parts. We're going to write it as NH4 plus, and we're going to write it as Br minus. Now notice the pattern here for the salts. You have 2 species. Remember what we said about salts? They could be acidic or basic depending on each of the 2 parts. So NH4 plus, we're going to try to, this is not going to be some crazy material that just comes out of nowhere. NH4 plus is almost the same as NH3. It's the conjugate acid of NH3. Right? It's the conjugate acid of NH3. Now, bromide is the conjugate base of HBr, right? So no effect on acidity. This one's going to be basic. I'm sorry, it's going to be acidic, right? It's coming from a weak base, so it's going to have an effect. Okay, now we know this one's basic. And we know this one's acidic. Okay. So now let's go through the reaction here. What's going to happen? You have to decide what's going to happen. We're adding HNO3 to 2 different things. One's a base, one's an acid. So you have to ask yourself, this is a new idea. We haven't covered this. If I add an acid to a mixture of both an acid and a base, we haven't looked at that before. What happens? Try a little picture here. So if I've got a little acid in here and I've got a little base, and I start adding an acid to it, we'll call this acid 1, this is acid 2. What's acid 2 going to do? Acid 2 is going to pretty much ignore acid 1. Acids don't react with each other in general. There are some exceptions to that. But acids will react with bases. So what will happen is acid 2 will react with base to give you water and a salt. All right. So what's going to happen here is when you add the HNO3, that's your acid 2, to NH4 plus and NH3, HNO3, the acid 2, HNO3, is going to react with the base. So HNO3 will react with NH3. Okay. Why? Because this is an acid and this is a base. So we're just going to ignore NH4 plus Br minus for now. All we're doing is we're looking for what is that acid that's being added going to react with, and that will always be the base. An acid will always react with base. So treat this as a regular acid-base reaction. Donate the H plus, so you get NO3 minus, and you get NH4 plus. Okay. All right, so this is our conjugate base, conjugate acid. Now, what do? Put the numbers in. 0.43 moles. The amount of NH3 is 1 liter, 1.2 moles per liter, or 1.2 moles, right? However, in this particular example, we actually have some ammonium already. 1 liter, 1.2. It said both. Both are 1.2 molar. So we also have 1.2 moles here. That's 0. There was no nitrate to begin with. So isn't this interesting? This is the common ion effect, which is that we have ammonia and ammonium. So ammonium was already in there in the form of NH4Br. But now this reaction is going to produce more ammonium by reacting HNO3 with the NH3. So that NH4 plus is a common ion. It's interesting. So which one's limiting? The smaller, so minus 0.43. This will go down to 0. Minus 0.43. So that's what, 0.7, I guess it was 1.2 minus 0.4 would be 0.8, so 0.77. Okay. This one is going to go up 2. So it'll go up to 0.43 mole. This one didn't start at 0, though. It started at 1.2, so it also goes up by 0.43. So you get 1.63. So notice we have 3 different things in here at the end, and that's not even including the Br minus. The Br minus was also in there, right? Okay. So now let's figure out what we've got. Well, this is a weak base, right? This is the conjugate acid of a weak base, so it's a weak acid. Right? Weak bases give weak acids. Strong acids give no bases at all. Okay. So now we've got NO3 minus. This is the conjugate base of a strong acid. So it's neutral. Okay, so now we can come back up here. Let's do our acid, base, and then other. Okay, so we have a weak base, which is NH3. We have a conjugate acid, which is a weak acid, NH4 plus. And then we've got an other, which is NO3 minus. But it's easier to forget that there was also some Br minus in there, right? So the Br minus has no effect on the acidity. So there you go. Okay, that's a little involved. So you might want to watch that video a second time if you're having problems with it, but take a look at it. It's an interesting problem that'll lead us into buffers. Okay. So we're going to do another type of problem, which is related to this. So let me go ahead and show it here, because again, some of these problems are a little bit involved in terms of how they're presenting them. So let's take a look. So this is called setting up a reaction table for a pH calculation with a common ion. Okay, so we're not actually calculating the pH. We're going to do that in the next section, 17.2, but we're going to at least set up the table so that we can do the calculation. A solution is prepared that is initially 0.37 molar benzoic acid. So HC6H5CO2 is benzoic acid. And 0.34 molar in potassium benzoate, which is KC6H5CO2. Complete the reaction table below so that you could use it to calculate the pH of this solution. Use X to stand for the unknown change in the concentration of H3O plus, and you can leave out the symbol of capital M for molarity. Okay, so we're just going to go ahead and put those numbers in here. And what they're doing is they're taking the acid, then they're having the conjugate base, and then they're having the hydronium. So let's take a look at this one. A little bit awkward, but it's not an easy thing to present in a really streamlined way. So we have 0.37 molar benzoic acid. So H C6H5CO2. So there's your benzoic acid. And then there's also 0.34 molar potassium benzoate. Okay. So those are the two things that are being added, okay? So let's take a look at this. The general way that you deal with this is you take the acid, okay? We're going to assume that everything is soluble in water and react the weak acid with water. Okay. So take your acid and react it with the water. It's a common theme in these two chapters. We're just doing this a lot, where you just write the reaction with water, okay? So we have benzoic acid. Now, this is not the only way to do it. You could also do the reverse of it. You could take the potassium benzoate and react that with water, but that's okay. We're gonna do it this way, all right? So take your weak acid and you're gonna react it with water to form your conjugate base and your hydronium ion. Okay, now what they want us to do is to fill out this table. So I'm going to recreate this table here. And they had a little bit of a problem making it look nice. Okay, they're going to put initial here, change, and then final. And then here you're going to have concentration of HC6H5CO2. Hope I got that right. And then you're going to have concentration of C6H5CO2 minus. And then they're going to have concentration of H3O plus. Okay. So let's take a look at our initial. Our initials are right here. These are the initials. Okay, so 0.37. They said leave the M out. 0.34. Now this one is, the question is, what's H2O plus? Now, technically, it's going to be the value that water would have, which is 10 to the minus 7, but that's such a small number. We're just going to put 0 to begin with. Okay, so really what we're doing is we're saying, look, if you put these two species in water, which is the benzoic acid and the potassium benzoate, okay, what are the initial concentrations going to be? Well, it's what you put in, the initial that you put in, 0.37, 0.34. The hydronium, you haven't formed any, there's no reaction, nothing has really happened. So before you start getting anything, you don't have any, okay? So it's 0. Now, here's the thing. Remember, there's an equilibrium expression, right? You take the products multiplied together, divided by the reactants, right? And it's going to be greater than 0, right? It's not 0. We don't really have equilibrium constants that are equal to 0. It's going to be something. So what happens then is if this is 0 here, that means that it doesn't work out, right? You can't have a number 0 in that expression and have the whole thing be not 0. right? So here's what happens. These are going to have to go up, and this is going to have to go down by some amount, right? So this will have to go down, and these will have to go up. That's essentially what has to happen. The reaction has to shift to the right in order to come to equilibrium, in order to give us a value of K. So then at their final value would be 0.37 minus X, 0.34 plus X, and then 0 plus X is just X. So Ka would be 0.34 plus X times X over 0.37 minus X. Okay, in general, this can be approximated to just 0.34 times X over 0.37. They're not asking us to do this step here. You don't have to do this step that I'm doing down here, but we will do those types of problems later on. So in any case, that's how you would use this table. You would then have your 0.37, 0.34 and your X, and then that would be equal to Ka. That expression would be equal to Ka. Okay. Now, what about the K plus, the potassium? They're putting in potassium benzoate. So what about the potassium? Well, remember, potassium is K plus, right? Potassium is the conjugate acid of a strong base, which means it has no effect on acidity. So it's in there. But notice a lot of these problems, sodium and potassium. So you're putting in potassium benzoate or sodium benzoate. Sodium and potassium are the conjugate acids of strong bases. So they're in the salt, but they have no effect on acidity. That means we don't need to worry about them in the equation. We don't need to worry about them in the calculation. The only thing that matters is the conjugate base of the benzoic acid, which is the benzoate part. Okay, so the benzoate is what's going to affect the acidity. So let's take a look. Oh, and I do want to point out, the reason we're going through this is that all three of these affect acidity. This is a weak acid. This is a weak base. And this is an acid, right? So they all affect the acidity. So that's why we're taking all three of those into account, but we don't have to worry about the potassium. Okay, I'm going to show one more here. Okay, setting up the reaction table for a pH calculation with common ion. Okay, so a solution is prepared that is initially 0.40 molar in methylamine, CH3NH2, which is a weak base. Keep that in mind, it's a weak base. And 0.19 molar in methyl ammonium chloride, CH3NH3Cl. Complete the reaction table below so that you could use it to calculate the pH of this solution and use X to stand for the unknown change in concentration of hydroxide. You can leave out the capital M, symbol for molarity. And then there's our table there, okay? So this one, it's a very similar problem. It's just we're gonna use ammonia in this reaction. Or I'm sorry, not ammonia, but a material related to ammonia. So we have 0.40 molar methylamine. I'm going to really write these all out so that you can review it. Methylamine is CH3, which is methyl. I don't need to put dash there. Kind of naturally do, but you don't need it. There's your formula. Okay. Which is a weak base. They tell us that. We should know that's a weak base because it's got that NH, right? Anything that has the NH is going to be a weak base. We've also got 0.19 molar methyl ammonium. It's a very long name, so I'm going to write the chloride underneath. And that is CH3NH3, Cl. They don't tell us what that is. However, if you have a weak base and it's going to be in water, it is going to produce some conjugate acid. So this right here is the conjugate acid of the methylamine. So there's your conjugate acid. Okay, CH3 NH3 plus, right? The chloride is in there too. But that is the conjugate base of a strong acid. So just like sodium, potassium, we can ignore them in terms of acid-base properties because they are the conjugate acids of strong bases. Chloride, bromide, iodide, we can ignore their contribution to acidity because they are the conjugate bases of strong acids. However, the methylammonium ion, methylammonium, that is the conjugate acid of a weak base, so it will behave like a weak acid. So now let's go ahead and write out the initial, change, and final for this particular process. And then I'll actually write the equation underneath. I just want to point out we're doing exactly the same or similar to what we did in the previous example. Okay, so they put in here that's an NH2, sorry. Concentration of those. Now, what's the, well, I'm going to write them out here. Sorry. There you go. Okay. So notice how in this one, they give you the hydroxide. They don't give you the hydronium. So here's what you do. If they give you the hydroxide, take the base. React it with water. Remember, it's a weak base, so we use the equilibrium expression. The water donates an H plus to the weak base. So you get CH3, NH3 plus, and water losing an H plus gives you OH minus. Okay, so let's put in our numbers here. The initial amount of methylamine is 0.4. The initial amount of methylammonium is 0.19. And again, just like the previous example, this one starts off as 0. Now, notice this is Kb, right? We're doing the base from the perspective of the base. So we're going to have two products. And one reactant. Oops. Okay, the base goes on the denominator, in the denominator. Okay, it's got to be greater than 0. It's a weak base, so it's got to have a Kb value. It's going to be small, but you know, it's probably 4.4 times 10 to the minus 4, something like that. But it's greater than 0. So the point is, if this is 0, that doesn't work out. It's got to go up. So if that's got to go up, then this one's got to go up too, right? Because they're on the same side. And this one's got to go down. Okay, so this will go down, these ones will go up, and then it'll reach the value of 4.4 times 10 to the minus 4, whatever that happens to be the Ka value. It might be 4.4 times 10 to the minus 5. You can look it up. So this starts at 0.4, but it goes down by x. This starts at 0.19, but it goes up by x. And this starts at 0, but it goes up by x. So that's just x. So now Kb would be the products 0.19 plus x times x, right? Hydroxide is x, divided by 0.4 minus X. Now, again, it is a relatively weak base. So this can probably be approximated as 0.19 times X, right? So I'm just getting rid of the plus X there, and then 0.4. Okay. So there you go. So there's another example of that. Okay. So if they give you the hydroxide part, like they did in this one in the table, then do the base reacting with water. If they give you the H3O plus, then take the acid and react it with the water. Okay. And there you go. So there are a couple of the pretty involved problems, but they're going to lead us into the calculation of buffers. So we'll get into that in 17.2.